We're going to study now the hydration of alkenes and alkynes in contrasting these two reactions. So let's do first the alkene, and then we will compare. In the case of the alkene, let's draw one. Again, I'm going to be using cyclohexene and substitute it. So the mechanism is similar to what we observed in the hydrohalogenation. So if we use, and here you will see, for example, one condition is diluted acid, but you can also see this as your reagent, sulfuric acid, like in brackets, diluted. So what happens in the hydration is similar to the the mechanism that we study in hydrohalogenation. So I'm going to draw the hydronium here, and what we do is pi electrons are going to be acting as base. I'm going to get the proton, and this is going to be protonated in Markovnikov fashion. Markovnikov. So the reuse selectivity here is Markovnikov, because if you add that H here, then you will be creating a carbocation that's more stable, more substituted. That's your intermediate. That's the same what we observed before. And that's your intermediate. And in the hydration, then you will have, this is diluted acid. Your nucleophile is going to be water. You form another intermediate that here you will have a positive oxygen, so an oxonium. And in the last step, say, water acting as base will be removing this H, and you end up having an alcohol. And again, this is your Markovnikov hydration. So the hydration of alkanes, we will see several conditions. So this is one. So what happens in the case of alkenes, when we have intermediates that are open carbocations, sometimes they can't rearrange. Okay, the second condition that we will be studying here is using another reagent to prevent carbocation rearrangement when that's possible. So in these intermediates we have seen before, these are common intermediates also in the SN1 and the E1 reactions. So, but here they are in the hydrohalogenation in hydration Markovnikov. So the reagent that we're going to be using to prevent rearrangements is, we're going to be doing mercuration, demercuration. So here, this is the reagent that you would see. So mercuric acetate, and if it is hydration, that's your nucleophile right here. So in the second step is that demercuration, and for that we use sodium boron hydride. So it is Markovnikov, and you will not have the rearrangement. The reason why you don't have a rearrangement is that you don't have an open carbocation. In this case, you form an intermediate that looks like this. Here's a metal. Here is the mercury, and OAC, that's positive. So that intermediate prevents rearrangement, which will happen in the case of an open carbocation. In the second step, first step is intermediate formation. Second step would be the nucleophilic attack. The nucleophile is water in the case of hydration, and you will have the attack at the more substituted carbon here in your intermediates. So this is your attack. And bottom line, notice that the oxygen is going to be where the metal is. So you get the same alcohol. Later on, when you, this intermediate, when it opens up, you will have, say, if you had attack in the back, this is O. This is your metal, which we had there, and then we will have this, but this is removed in a later step with sodium boron hydride. Point is, this is where you get, and this will be removed, and you will put an H here, so you get in this. and removing that extra H. Point is that we don't have rearrangement. So that's your reagent. No rearrangement. And the third condition that we have in alkenes when we do hydration, these two are Markovnikov. These two. You can have rearrangement with the first, but if you don't have that problem, let's use that. But if rearrangement is possible, then you will use mercuration, demercuration. The third condition that you want to be using is when you want to prepare the anti-Markovnikov alcohol. In that case, for dehydration, you will use hydroboration, oxidation. So BH3 with THF, and second is oxidation, so hydrogen peroxide, and this is basic condition. What we need to remember when we're doing this reaction is that we will add anti-Markovnikov. So one thing, so anti-Markovnikov, and also the addition is seen. So you are adding, let me write it down, anti-Markovnikov hydration, and also is a zinc addition. What that means is that you need to have the OH and the H at the same side. So let's draw your product. So anti-Markovnikov means I'm going to put the H here and then the OH on the other side, which will be, is say that I have the metal here. If I have the metal there, then the H is here. And for now, I'm going to be drawing the H because we want to remember that this is a zinc addition. So these two need to be on the same side. This plus the enantiomer. Now, typically you will not see this drawn this way. So we will have, you don't draw the, let's draw it on that side. So you will not draw the H, simply this. That implies, if this is a metal, implies that the H is on wedge. And here you will have the OH on wedge as well. So that's your zinc addition product. So that plus the enantiomer. So this inverted, this inverted. Okay, so we have three conditions for hydration of alkenes. In my next video, what I'm going to do is show you the two conditions that we have for hydrations of alkynes and how that compares to this.